Okay, well, thank you very much. It's great to be back here in Manhattan at Kansas State University. I always enjoy coming back. So in order to prepare for this presentation today, I decided to reflect back on some of my past seminars I've given in front of all faculty, all students in this department, and use that as a way to prepare for today. So in total, this is actually my 9th time that I've given a seminar here for the Department of Statistics. And through looking through my past presentations, I noticed I had some trends, such as I'm often very excited. I like to include exclamation marks, or I like to ask questions in the titles for my presentations. And I guess this is what actually led then to me combining the question mark and the exclamation mark together into what's called an interrobang, in case you've never ever heard of that term before. But also I noticed some other trends that often I like to have some kind of attention getter at the very beginning of one of my presentations. So for my very first presentation I ever gave was in July 1996, my master's report defense. And for that defense, I decided to show a video of a field goal kicker kicking a field goal. In this case, it was Kansas City Chiefs field goal kicker missing a field goal at the end of a game, leading the Chiefs to lose their playoff game and end their season. Hopefully that does not happen this year. Another time I gave a talk on one of my internships that I had when I was here, and I spent my entire summer basically trying to figure out what exactly was inside a Sunny D juice container. After I graduated in 2000, and I came back here in 2003 for the first time, I decided to show that now that I don't have to study all the time, I have time for other fun things. So here's myself with my major professor, Tom Logan, former faculty member here, and Conan O'Brien hanging out one evening. And the last time I was here was about 10 years ago. And I decided to talk about how not only could my research solve amazing real-life problems, but could also be used to solve those problems in science fiction, in particular one that dealt with the TV show Battlestar Galactica. So keeping with those trends, I decided to begin with this picture here. Does anyone know, and by the way, these two guys here, they're not like getting ready to fight. They're just like really excited about something. Does anyone know who these two guys are? Exactly. They are the Chris and Martin Kratt, aka the Kratt brothers, and they host a TV show called Wild Kratts. This is one of the most popular TV shows out there right now, in case you don't know. It's actually on PBS in their PBS Kids programming. And just to show you how popular that it can be, here's, for example, my kids, before going out trick-or-treating, actually this is from a couple years ago, they were dressed as the Kratt brothers. And so, for those of you who are not familiar with the show then, what the show is about learning about animals and all the interesting, unique abilities of animals. But these guys go even farther than, let's say, just talking about an animal. They say, imagine, to the audience, they say, imagine if you were an elephant, what would it be like? Or imagine if you were a whale. Imagine if you were a rabbit, what would it be like? And then they say, well, what if? And they turn themselves into cartoon characters so that they can actually, in a cartoon sense, experience what it would be like to be a whale, an elephant, or a rabbit. Now, the reason why I'm introducing you to the Wild Kratts show is not because I am now going to turn myself into a cartoon character and give the rest of my seminar like that. This is actually the PhD Comics representation of me, if you've ever heard of PhD Comics. Rather, what I'm going to do is talk about this what if part. Yes?
How did you get them to give you other presentations?
Well, they had like some kind of crowdsourcing for their second movie, and I donated to it, and one of the prizes I got was a cartoon representation of myself. It's actually now on my website too. And so we're going to talk about this what if part. And the other day when I was watching the show with my kids, as I do pretty much every day, the Kratt brothers got to the what if part. And then I started thinking, you know what? When I do my research, I always ask, what if? What if I tried to use some other kind of estimator to do something? Or what if I tried to derive something a certain way? Or what if, for infectious disease testing in humans, suppose we use a method called group testing with multiplex assays to make the testing process more efficient, because we do millions and millions and millions of HIV, hepatitis B, West Nile virus, chlamydia tests every year. What if we could lower the number of tests so that we can make it more efficient? And so what I'm going to talk about then today is how I answer, or I'm still trying to answer that question of what if. So for those of you who are not familiar with group testing, I would expect probably most of you, what group testing is the process of testing items together as one unit, or a group or a pool. In other words, imagine you had a number of blood specimens from people. What you could do is you could combine them together into a group or a pool and perform one test on that group. And you do this rather than testing the individual items separately or individually, where the purpose is then to identify, well, which items have a particular binary trait. So with respect to an infectious disease, it would be, are you positive or are you negative for a particular disease? To give you an example of where group testing actually is used right now, what I have here is some pictures showing showing how chlamydia and gonorrhea testing is performed by the State Hygienic Laboratory at the University of Iowa. So every day, this laboratory receives specimens, either urine or swab specimens. They arrive in test tubes, as what you see there. They arrive at this lab, and they need to be tested for both of these infections. So one of the first things that's done is that these test tubes then are transported into their laboratory, and they are mounted on a rack. And you can kind of see, here's a rack of test tubes right there. They're actually going to add another one to that. And what this is they're robots that actually, and you can say automatically, forms groups of size 4 for these specimens. And so I actually have a video showing the process, just to demonstrate it to you. So what you see on the right-hand side is that you see some arms, robotic arms coming down. They're getting some pipettes. They go down into the specimen tubes. They draw out about 700 microliters. They draw it out, and then eventually what they're going to do is go then to a empty test tube, and they're going to put that 700 microliters right in there, and then they're going to deposit the pipettes. And then they're going to do this for other specimens, as you will see. So some new set of specimens, they're going to go down there, suck out 700 microliters, and where they're going to then put that is in that, originally that empty test tube. So once that's done, now we have essentially a group or pool size 2. And they're going to do this 2 more times, so we have groups of size 4 formed automatically like this. Okay. Oops, let me turn that off, sorry. Pause. Once they get these test tubes with these pooled specimens, they put them into this another kind of automated machine that is called a Panther system that actually then performs the chlamydia and gonorrhea test. And they use what's called the Aptima Combo 2 assay for it. What's interesting about this is this simultaneously tests for both chlamydia and gonorrhea at the same time. So because of that, it's referred to as a multiplex test. The actual testing process itself, from getting the specimens and forming the pools to getting final results, actually takes an entire workday. So to summarize, here's a very crude diagram showing what's going on. Pools or groups of size 4 are formed, and for every single pool, we get a positive or negative result for chlamydia and also for gonorrhea. Now, the reason why the State Hygienic Laboratory does this form of group testing is because if a group tests negatively for both diseases, then all individuals within it can be declared disease-free. So notice it only took one test to determine that 4 people are disease-free, rather with individual testing or testing them separately, it would have took 4 tests to determine that 4 people don't have these diseases. Of course, though, if a group tests positively for at least one disease, then you need to determine, well, who's positive, who's negative, and for which disease. What the State Hygienic Laboratory does, and you see this in other places as well, is that they'll simply just retest all individuals, separately, and they use the exact same assay with it. So what we see here is essentially a 2-stage testing process. You test in groups. If positive, then you go to a second stage and you test individually. Now, the reason why this, let me back up for a second. So these particular diseases, fortunately, are somewhat low prevalence. So in Iowa, we're talking in terms of the specimens that they test, chlamydia might be about 10%, gonorrhea might be about 3%. So low prevalence diseases. So what this actually will mean is that most groups will actually test negatively for both diseases. Because of that, then, that's going to lead to a smaller number of tests overall than if you would have began with individual testing at first. Smaller number of tests then means lower costs. It's also going to take less time to do the testing. Over a recent 5-year evaluation period, the State Hygienic Laboratory estimates that they've saved about $3 million by implementing group testing. The same process is done all across the country, and mostly it's used with this particular assay, where it's a multiplex assay. Now, there are many other examples of where group testing is used. Probably the biggest place where group testing is used is with respect to blood donation screening. So obviously, any kind of blood that's donated needs to be tested for various diseases, so it's not passed from the donor to the recipient. And so what the American Red Cross, for example, is for a number of diseases that they test for, they use groups of size 16. It's also used in animal applications as well. So for example, a big one is bovine viral diarrhea virus, where group testing is used. But it's used in many other non-infectious disease testing, such as, for example, drug discovery, trying to determine what chemical compounds might be potent to hopefully, let's say, end up being developed into a pharmaceutical product that could be that could cure a disease. So, as I mentioned before, the Aptima Combo 2 assay is a multiplex assay, and so what we see is that more laboratories are going towards using these rather than single disease assay, where you test for chlamydia separately from gonorrhea. And the reason being because, of course, you're going to save time and money, so you don't have to do things separately. And there are many other kinds of multiplex assays out there. So, for example, one that's frequently used for blood donation screening screens for HIV, hepatitis C, and hepatitis C all at the same time. The company BD just recently, about a year or so ago, released a new multiplex assay for chlamydia, gonorrhea, and trichomoniasis. And there's many other assays being developed right now. So one that's not available here, but it is in Australia, is for chlamydia, gonorrhea, and mycoplasma genitalium, or MGen for short. Now, perhaps surprisingly then, only recently has statistical research really investigated how these multiplex assays can be used most efficiently in a group testing setting. Group testing has a long history of research. For example, back in the 1940s, was often thought of as one of the first times where somebody proposed to test initiates into the Army during World War II to pool them or group them to test them for syphilis. And so only recently has statistical research really investigated these multiplex assays via these group testing algorithms. And so myself and my colleagues, Josh Tebbs at the University of South Carolina and Chris McMahon at Clemson University, we were the first. We had a paper in biometrics where we focused on that testing algorithm that's used by the State Hygienic Laboratory. And that's what earned us the Outstanding Statistical Application Award in 2014. we decided to try to capitalize on that award, and we decided to put together an R01 NIH grant, and eventually we were able to get that funded. And one of the first papers that has come out of it appeared in 2017 by us in Biometrics, where simply, what if you did more than 2 hierarchical stages? So for example, here's how HIV testing is often done in San Francisco, where you start off with an initial group size of 50. So you combine the specimens, initial group size of 50. If you have a positive, if it tests positively, then you go to a second stage where you could have, let's say, 5 groups of size 10. And if any of those groups test positively, you go to a stage 3 where you can go to individual testing. This paper then was what won us then the Best Paper in Biometrics Award this year, and also the Outstanding Statistical Application Award. Now, getting these awards is great, but whenever you do research, very often you're like, I think I can do better. Now, I wish maybe I didn't make this assumption. Maybe I could generalize it somehow. And that's the way we felt coming out of those particular papers. And the main limitation our paper had, or I don't want to call it limitation, but something we didn't like, is that the previous research assumes every individual has an equal probability of being positive for a particular disease. So all individuals have the same probability of being positive for chlamydia. All individuals have the same probability of being positive for gonorrhea, for example. So then we were wondering then, well, what if one could differentiate amongst individuals who are at, let's say, higher risk for disease than others? So you could imagine, because of certain risky behaviors, some individuals might be at more risk than others, or maybe symptoms that present themselves when they go to a medical clinic to get tested. You could use those symptoms to help differentiate amongst certain individuals that were more likely to be positive. So when one does that, then you then do what we refer to as informative group testing. And as you might imagine, that if you use this extra information, your testing is going to be more efficient, meaning you're going to lower the number of tests that are needed. And indeed, that's what we showed in a number of papers, but we focused always on single disease assays at that time, so that's what we were more familiar with. And I should mention that maybe I didn't say something earlier quite well, is that all previous group testing research always focused on single disease assays. An interesting side note, so the last time I was here 10 years ago, I was just starting to develop this informative group testing ideas. And it eventually then turned into a JASA paper. And so I guess that's one reason also why I thought I'd kind of reflect on what I've done in the past. It's kind of interesting now to see how things have progressed over 10 years. So given we know about informative group testing, but it's only for single disease assays, you might think, well, what if then we develop informative group testing algorithms for multiplex assays? And we're going to continue using this hierarchical structure. So for the rest of my talk here, I'm going to talk about a paper that actually I just had accepted by Biometrics in October that basically talks about this. Okay, so now we get into the more real statistics part of the talk. So the reason why I like group testing research, especially with multiplex assays, is because there's an interesting stochastic framework here. And then as we are working with unobservable, correlated, binary random variables, which represent the individual disease statuses of those people who are being tested. So the binary part comes into play because either you're positive or negative for disease. The correlated part comes in because now we're using multiplex assays, and what you have a result for one disease might be correlated then with another disease. And then the unobservable part comes into play because these assays are not 100% accurate, unfortunately. So if you went and got tested for an infectious disease, let's say it's HIV, and it comes back negative, well, guess what? That test is not 100% accurate. It could actually be positive. It's a low probability, but at least for the way HIV testing is done, but it is possible. And so we never actually observed then these individual disease statuses from the assay itself. So let's now talk about some notation. Let's let y tilde sub ik be the true binary status, where I always will use 1 for a positive, 0 for a negative, for individual I and disease k. And what we're going to be very interested in is, well, what's the joint probability of disease for individual I? We're up to, let's say, k, capital K different diseases. So, for example, when we only have 2 diseases then, here are the 4 joint probabilities of disease. So P sub I00 is the probability that individual I is negative for disease 1 and for disease 2. And if you turn things around, look at 1 minus P sub I00, then we have something that actually ends up being very useful, and that is the probability of positive for at least 1 disease. Remember how the State Hygienic Laboratory does their tests. If you're positive for at least 1 disease, you're going to go to the next stage of testing. So you might think then in this scenario too that large values of this 1 minus P sub I00 indicate high risk. Well, why not just maybe treat those individuals differently from those who are at low risk when you're actually doing the testing? Maybe again you could come up with a more efficient testing process. In the end, eventually these probabilities can be easily estimated. So let's consider that we have one initial group that we're working with, not a size 4, but let's say a size I to be general. And we're going to let G sub Sjk be the actual group test result for the kth disease in group J at stage S. We're going to let C sub S be the number of groups in stage S. M sub Sj be the number of subgroups that group J at stage S is divided into if it tests positively for at least 1 disease. And we'll let capital S be the number of hierarchical stages that we're working with. So going back to that diagram that we saw before, and I apologize if some of that is a little bit small, we start with an initial group size of 50. And from that group tests, we get responses for G111 all the way down to G sub 11K for that kth disease. If that tests positively, we go to the second stage. We have group sizes of 10. Note that there are actually 5 different groups that are formed. This corresponds to M11 equal 5. And again, for each of these groups, we're going to get K different responses from that. There is no more testing done after individual testing because you're done. You've already tested them individually. So M sub 3, then 1 up to M sub 50 is equal to 0. Now, to also present some stuff in a more concise manner, especially on the next slide, I'm going to need to define something called an ancestor group. And these ancestor groups are basically groups of prior stages that led to the testing of group J in stage S. So remember, you got to test, let's say, positively in group 1 in order to get to the testing in the second stage. So for example, if we focus on this particular group here, this is group 1 of stage 2, its ancestor group is this particular group here. So not only could I denote its group responses like this, but if I take this ancestor notation then, I can denote it like this as well. Excuse me, that should be a 1. So all it is a way for me in that superscript to say, okay, if I'm at stage 2, group 1, where would I have been on stage 1 for those individuals that were in that group on stage 2? That's all. Just a way for me to go back and forth. Now, with any kind of group testing algorithm, you want to know, well, how many tests will it take? Ideally, of course, you want the number of tests to be less than the number of people that are tested initially, that I, for example. So let's let T then be a random variable denoting the number of tests corresponding to the initial group of size I. So depending upon who's in that group, T is going to vary from one group of initial group of individuals to another. So T is a random variable. And what we're going to be then interested in is, well, what would the expected number of tests be from applying this particular algorithm, since T is a random variable? And so if we look at the case of 3 or more stages with an initial group size of I, this is what we get for that expected value of T, or at least one way to write it out. So you first test that initial group in stage 1, always. And then you're going to sum over all the stages except for the last one, because no more testing is done after the last one. Sum over all the groups within each stage. And what you're summing is the number of tests that will be needed if group J in stage S tests positively. What's the probability that it's going to test positively? That's what this large joint probability is just representing. It again allows you to see from group J, stage S, that group all the way into the past, you could say, the ancestors. So this would be the ancestor in stage 1, the ancestor in stage 2, and so on. And I do want to mention one other thing, because I forgot to mention this on a previous slide. Oh, I guess we'll just go to the previous slide to do this. Let me do some erasing here. Okay. So if I come over here, so in this initial group of size 50, again, if that tests positively for at least one disease, you're going to go to that second stage. So in other words, if G11 plus, where I'm summing over that third subscript, which is for disease 1, disease 2, up to disease capital K, if that ends up all being greater than 0, that says you have tested positive for at least one disease. And so then when I show you this expression for this joint probability, it makes a little bit more sense. So in stage 1, you tested positively for at least one disease, stage 2, and so on. Okay? Now, this joint probability, it can be difficult to find. Well, I shouldn't say difficult. It's just, I think I actually used the word in my paper. It's a laborious derivation. So in the end, it actually took me 6.5 pages on in my single-space web appendix to do the derivation. The actual final form of it will not fit in on one slide, unfortunately. So unfortunately, I'm going to wave my hands here a little bit and say, yes, you can find that. And it's dependent upon the actual testing configuration that's used, meaning are you going to use, let's say, initial group size of 50, maybe initial group size of 25 instead? Or what should the subgroup sizes be in stages 2, 3, and so on? It's dependent upon how good that assay is in terms of the sensitivity and the specificity. How good is it in getting the positives correctly? How good is it getting the negatives correctly? It's also dependent upon those joint probabilities of disease that we saw earlier. So for every individual in the initial group, it's dependent upon those corresponding probabilities. So if we have a way to calculate the expected value of T, then you might be then wondering, well, maybe I can use that to figure out, well, what testing configuration to use. A testing configuration that has the smallest number of expected number of tests probably be better than any other testing configuration. And there's some other factors to worry about too, but you want to have as small a number of tests as possible, because each test costs money. And so, well, which testing configuration will lead to the smallest or the least number of tests? So you're going to need to look at things like group sizes. What's the initial group size? What should be the subgroup sizes? Should I use 5 groups of size 10, or 10 groups of size 5, or 10 groups of size 5, or maybe 25 groups of size 2? What should you use? How many stages? Should I use 2 stages? Should I use 3 stages? Should I use 4 stages? And which individuals should I put in what subgroups? Because you can control that. Maybe you want individuals that have a high probability of disease separated out, for example, from those that have a low probability of disease. So what we want to do then is choose a testing configuration that minimizes the expected number of tests per individual. In other words, minimize the expected value of T divided by I. And so what you could do then is actually examine all possible testing configurations out there, calculate expected value t divided by I, and pick the one that does that. Guess what? There's a lot of different testing configurations, a lot. It depends upon what I is, of course, and the number of stages. But there's a lot. And so to somewhat limit what I'm going to search over, I'm going to use the following. I'm going to order my individuals in that initial group of size I by their probabilities of being positive for at least one disease. So I have maybe those who have low probability here, those with a high probability over here. Then what I'm going to do is sequentially assign these individuals to corresponding subgroups in, let's say, stage 2. So those individuals over here that have a low probability are going to be put together in a subgroup for testing, like in stage 2. Those with a higher probability will be put together over here in a subgroup. And also, I can control those group sizes too. So those over here probably should have a low group size. These over here could have a high group size because their probability of testing positively is low. And so that's how I'm going to approach this, and then search for all possible testing configurations that fit that criteria there. There's still a lot, but it's doable. Corresponding to these two parts here, there is some intuitive justification for doing it like this, and also a little bit of mathematical justification too. I have not been able to prove mathematically beyond any doubt that this is the best thing to do. Okay, but if there's interest, if you want to talk about it more after when I conclude here, we can talk about some of that justification for doing that. So then the testing configuration that minimizes expected value t divided by I, I'm going to call that my optimal testing configuration, or OTC for short. That's what a lab would like to use if possible. So I showed you the expected value of t for 3 or more stages. Well, what about just simply 2 stages, like what the State Hygienic Laboratory does? Well, what you can do is actually take advantage of the hierarchical structure that's in this testing and think of it as being equivalent to 3-stage testing, where you don't initially do that test in stage 1. So in other words, stages 2 and 3 become 2-stage testing. So for example, here's this diagram once again. And so what you can do is, imagine you're in a laboratory and you got these first 50 specimens come in. Okay? Don't group them together, but instead, how about you first break them up into 5 groups of size 10 and do testing that way. And so that this becomes now stage 1, and then if necessary, this becomes stage 2 as well. Now, for these 50 individuals though, what you're actually still doing is you're still ordering them by their individual probabilities of disease and sequentially assigning them to groups, not necessarily 5 groups of size 10, but perhaps something else. And that's the only way that you can take advantage of this kind of information when you do this kind of a 2-stage process, is that you think of sets of individuals first. So if we now let T be the number of tests for this initial set of I individuals, this is what the expected value of T looks like. It's quite simple. You have C1, in other words, the number of tests in stage 1, plus then the number of individual tests that will be needed if group J in stage 1 tests positively, and then we multiply it by the probability that it is positive for at least one disease. And then for using these I individuals, you could also find the optimal testing configuration as well. Again, these assays are not 100% perfect. So you might be worried about, well, how accurate is the group testing algorithm in its implementation? Is it going to find true positives as well as maybe some other algorithm? Yesterday when I was going over this part of my talk, I decided, I need to cut down. I need to reduce the time length, so I decided to skip the discussion. But I will mention this, is that there is no loss in accuracy compared to using, let's say, non-informative group testing. In other words, when you don't take into account that extra information that might be available to you. So that's good. And that non-informative group testing then corresponds to that 2013 and 2017 paper that I mentioned earlier. Okay, so let's take a look at some simulations then that examine how well this method works and when should it work. So we're going to focus on 3 stages, 2 diseases. I need some way then to come up with these individual joint probabilities of disease for this assessment. And so that's where I decided to actually simulate this from a Dirichlet distribution with parameter vector alpha. And the reason why I'm going to simulate these, again, imagine you have, let's say, I individuals in a group. You would expect them to have different probabilities. And so what this is going to allow me to do is control the heterogeneity that you would have of people within your group, because people have different risks of disease. So for my assessment, then, I'm going to simulate I observed values of this vector of joint probabilities of disease, and I'm going to repeat this then 500 times. I'm going to do this over a number of different cases. So first we're going to look at this particular situation where what I'm going to do is control the expected value of the marginal probability of having disease 1 and the expected value of the marginal probability of having disease 2 at 0.05. In other words, this is like saying, let's say the disease prevalence for disease 1 is 5%, the disease prevalence for disease 2 is 5% as well. This is when group testing is usually used in low prevalence settings. There are an infinite number of possible alpha vectors that will give me a distribution with this, this quality. So I picked this particular alpha vector for now. We'll see other alpha vectors later or shortly. And let's say the assay sensitivity and specificity are equal to 0.95 and 0.99 respectively. What I'm going to do is examine this expected number of tests per individual then relative to the variability in these marginal probabilities of disease. You know, what's going to happen with this expected number of tests per individual? Is it going to go up or down corresponding to the variability? In other words, how much heterogeneity there is within the group. Now I do want to mention here, and perhaps unfortunately I might have skipped over this. So this expected number of tests per individual. So we're very interested in the expected number of tests. The reason why I want to divide by I there is because let's say I have a group testing algorithm that starts with an initial group size of 100, and when compared to one that starts with an initial size 3. Well, that one that has size 3 is going to probably have a smaller expected value of tests. So by dividing by I basically take the number that you're starting with out of play, and so it allows me to do an equal, a fair comparison. So sorry if I forgot to mention that before. So I'm going to look at some cases of this variability. And for the lack of a better way to describe it, we're going to call the medium variability case corresponding to when I have this distribution with just alpha as its parameter vector. Then we'll look at a low variability case where if I take 4 times alpha, these variances will actually go down. Doing a simple calculation to find that actually will occur. Then if you were to divide that alpha vector by 4, it causes those variances to go up. So there's going to be more heterogeneity in your group of the individuals there. And lastly, suppose you have a case where there's no variability at all. Well, that again corresponds to what I refer to as non-informative group testing, where you're not using any information at all, and you're just saying every single individual has the same probability of disease. So this would be then equivalent to just simply using the expected value of P sub I as the probability for every single individual. So here's a plot that summarizes the results. So on the y-axis here, I have the expected number of tests per individual. Again, we want that to be as small as possible. Also, if you think of it in the grander scheme of things, if the expected number of tests per individual is greater than 1, then you shouldn't use group testing, because individual testing has an expected number of tests per individual of 1, because every single person is tested once. So you can see that these methods are doing better than what if you just did separate testing of every single individual. On the x-axis here, I have the initial group size for stage 1. Again, we're doing 3 stages overall. And so let's focus on this 10 here. So I start with the initial group of size 10. This triangle then comes about the following way. Suppose I take a sample of 10 individuals from this distribution corresponding to the high variability case. I find the optimal testing configuration for those set of realized joint probabilities of disease, whatever that testing configuration might be. I record the expected number of tests per individual, and I do that for my first, let's say, run of my simulation. Then for the second run, I do exactly the same thing. I do this 500 times, so that what I report in that triangle is the average over those 500 times. So the average expected number of tests per individual. And so we see it's about 0.45. So you save, compared to individual testing, about 55% in tests. Now let's compare that to medium variability, low variability, and then no variability at all amongst those probabilities of disease. And what we see is that informative group testing works better when there's more heterogeneity in that group, because you can distinguish between those people who are at higher risk versus those that are at lower risk. And we see this occurs across any initial group size that you were to choose. Well, what do those testing configurations then look like? Well, what I have here is a stacked bar chart, where on the x-axis, again, I have that stage 1 group size. On the y-axis, I have this possible stage 2 group sizes. So for example, when there was no variability at all, there's no simulation here, we see for an initial group size of 20, there are 5 groups of size 4 being formed in stage 2. Now compare that to the low variability case, the medium variability case, and the high variability case, and you can see what's happening to those second stage group sizes. They're changing. Also, let me remind you that people are put into these second stage groups by the first group becomes the low probability of disease group. The last group is the high probability disease group. And that's what's represented on this plot, where this bar here that has about a size of 8, this is across my 500 simulations. That first group that's being formed, on average, has a group size of 8. And these contain those people with low probabilities of disease. The groups up here correspond to the ones that have the high probability. Again, this is average over the 500 groups. So let's take a look at an application. Ideally, what I like to do is get my hands on some specimens and actually implement different testing configurations on them simultaneously on the exact same specimens. And then choose then whatever method works best, whatever method that's most efficient. In other words, the lowest number of tests to fully decode who's positive and who's negative. Do that with actual specimens. Unfortunately, that's very impractical because of the expense involved. So for example, with the State Hygienic Laboratory, they estimate that per test it costs about $37. Also the time. You saw how long it took them to do just one set of tests, a whole workday. And then the volume of available specimen material is just not enough. So at most you could probably get 3 or 4 stages per, in at least the State Hygienic Laboratory case, per in terms of what's in that test tube. So instead, to try this out in terms of an application, what I decided to do was try to emulate how testing would actually be performed using some retrospective data that I had access to. So I have 2 years worth of actual chlamydia and gonorrhea testing data from the Aptima Combo 2 assay available from 3 states, Idaho, Iowa, and Oregon. And the type of information I have available in my data set are the final chlamydia and gonorrhea test results. For each individual, I have information about the patient's behavior that they reported on a basically a survey form when they came into the clinic to be tested. I also have information about clinical observations that were made by the medical provider when they were in the clinic. So using then that kind of information, then that provides me a simple way that I can then estimate then the individual joint probabilities of disease. So here's then a rough outline of how I'm going to do all this. What I'm going to do is use the earlier year that I have available to me as essentially a training data set, where I simply estimate a multinomial regression model to estimate these joint probabilities of disease. And then I'm going to approximate one optimal testing configuration that will be best across the entire year. Unfortunately, I don't have time to get into the exact details of how that is done, but it uses what's called a non-adaptive approach, proposed by one of my PhD students, Michael Black, back in 2015 for single disease assays. And the main thing is basically just how I talked about how to find an optimal testing configuration before, but now just kind of extend it over multiple initial groups. But it's basically the same concept. So for example, for Idaho females that are being tested, this is what the optimal testing configuration will look like over 3 stages. Start with initial size group of 8, then stage 2, go to groups of size 4, 3, and 1, and then individual testing as needed. Then what I'm going to do is then use the later year as a test data set. So using that trained data model, I can estimate then the individual joint probabilities of disease for that later year. I can apply this optimal testing configuration to, in this case, this example here, consecutive individuals that are coming into the laboratory, 8 at a time, in terms of their specimens coming into the laboratory. And then, unfortunately, though, I still need to somehow take into account that these assays are not 100% perfect. So I have to actually introduce some kind of Monte Carlo simulation to fully do this. So using the manufacturer reported sensitivity and specificity levels. So for chlamydia and gonorrhea, depending upon the scenario, might be 0.95. The lowest I've seen is probably about 0.92. Some might be 0.98 as how good this assay is. And what I'm going to do is treat, in my actual data set itself that I have, treat the final chlamydia and gonorrhea results that I had in the data set as, let's say, the true statuses, and then simply using a Bernoulli distribution, simulate what could happen during the group testing process of potential errors that could come about. Repeat this process 500 times. It's not perfect, but this is the best that I could think of how to do it. And so here's the results that I got. So we have the state, we have the gender, broken up by gender because these manufacturers report sensitivity and specificity levels by gender. We have the number of individuals that were tested, and we are going to look at what happens if we apply 2 or 3 stages. Then again, I'm averaging over 500 simulations. So if I were to use the old non-informative methods that were in my 2013-2014 paper for Idaho females, 2 stages, get about 2,200 tests to decode all 4,168 individuals to determine positive or negative. Now, when I use, so that's 2,200 tests. So when I use informative, then I get 2,100 tests. So a reduction of about 5% of tests. But this reduction can be more. So for example, for Idaho males, about 15%. And across here, we see some trends that, generally speaking, informative group testing works, meaning it reduces the number of tests compared to what was done before. And it works better for males than for females. Well, why? It has to do with that variability in those probabilities of disease that we saw in that simulation study. In that, for example, here are Iowa females. We have a histogram of all the p-hat00 values. In other words, the estimated probability of having no diseases. And for Iowa females, this is where informative group testing performed the worst in that previous table. And we see everything's kind of tightly clustered. Now compare that to Idaho males where it worked the best. We see a big difference. There's a lot more heterogeneity. There's more variability. And so that's why I work better for males than for females. Okay, so to summarize it, what if we use informative group testing with multiplex assays? Well, we see a significant reduction in tests where that reduction is works more, or there's more reduction in the higher variability cases, the higher variability and probabilities of disease. If you want to know more about group testing and also this specific work, you can take a look at my research website, chrismiller.com/group testing. And lastly, I'll leave you with this. In about 1 hour at 6 p.m., the TV show Wildcrats will be on the PBS affiliate out at Topeka. So you can go home and watch that. That's the end of my talk. Thank you very much.